Module 2.2, Momentum Transport. We're going to look at introduction, momentum transport, Newton's law of viscosity, application in one-dimensional momentum transport. Then we'll look at comparison between heat mass and momentum transport. We'll look at illustration and then conclude. Momentum is defined as mass of a substance multiplied by its velocity. Therefore, if a fluid is moving through a conduit and a velocity gradient exists, successive layers of fluid are moving at varying velocities and thus possessing varying momentums. So once the velocity is different, then momentum is also different. Fluid layers with higher momentum are bound to impact some to the slower layers through molecular interactions, just as in molecular heat conduction and mass transport. So the same thing we saw in mass transport will also occur in momentum transport. Another way of looking at momentum transport is to consider the classical case of motion of a fluid contained between two long parallel plates. Suppose the lower plate is stationary and the upper plate is moving with a constant velocity ux due to the action of force Fx. Fx, that's in the direction of x, the same direction. As a result of property of fluids known as viscosity, tangential or frictional forces exist between layers of fluid in motion. At the wall, intermolecular attraction causes the fluid to stick to the surface and therefore acquire the same velocity as the wall. We call this as no-slip condition. So the molecules close to the wall, if the wall is moving with a velocity ux, the molecules close to the wall will also move with a velocity ux. But if the wall is stationary, then the molecules close to the wall will also be stationary, and there will be a velocity profile as you go out from the or off the wall. So this idea of the molecules taking up the speed or the same velocity as the wall is what we call no-slip condition. In other words, the velocity of the fluid is zero at the stationary plate and increases to ux at the upper plate, giving rise to a velocity profile as shown in the next slide. Look at the velocity profile there. Towards the wall that is stationary, it is zero and progressively increases to ux, that is the velocity of the wall that is moving. So we can see the velocity profile, of course, because of shearing force. Thus, the upper plate moves at ux as a result of the applied force. We've said that, no slip condition. As a result of frictional force between successive layers of fluid, the next layer of fluid is pulled along, but at a slower velocity and so on. So we'll have that profile. The overall effect is the velocity profile we have there. Newton's law of viscosity. Of course, force is defined as the rate of change of momentum. So look at our Fx, equation 1, change of momentum with change in time. Remember we said momentum is mass times velocity. So the shear stress, which is the shearing force per unit area, is given by Newton's law of viscosity, which is tau. This kind of T is called tau, equal to minus mu gux over dy. And if we combine equations 1 and 2, we will have equation 3. And equation 3 clearly shows that the shear stress is the rate of change of a property, which is momentum per unit area, and is therefore a flux. Remember we met mass flux, density flux, and so on. The driving force for this flux obviously is velocity gradient. Look at it, the ux over dy. That's velocity gradient. So this is Newton fluids that obey this law are called Newtonian fluids, as we'll see later. We also have non-Newtonian fluids. Application in one-dimensional momentum transfer. Now, the driving force for heat and mass transfer, temperature and concentration gradient are scalar quantities. But when you compare it to the driving force of momentum, which is velocity, velocity is not a scalar quantity. You know, if you remember our scalar quantities and vector quantity, velocity is a vector quantity because it also has direction. Therefore, the complexity in this shear stress tension is that we're going to have 9 components. So because it's a vector, we're going to look at, there will be shear stresses developed, and we also have some normal stresses as outlined below. So Newton's law applicable in parallel laminar flow gives shear stress acting in x direction as that equation for law of Newton's law of viscosity. So which means we have shear stress over rate of shear strain. So looking at these, because of vector quantity, we are going to have 6 shear stresses and of course 3 normal stresses. That make it 9 components, different from scalar quantity because velocity gradient is a vector quantity. Now we want to look at heat, mass, and momentum transfer. Now if you compare the equations, we'll have some similarity. We'll have, they are all flux, gradient of driving force. Now the constant of proportionality for thermal conductivity, that's for heat, we'll have thermal conductivity. For mass diffusion, we'll have diffusivity D, and then for momentum transfer, that's Newton's law of viscosity, we'll have viscosity as constant of proportionality, if you remember all our equations. Now, in spite of this similarity, the equations there are still some, things we need to consider. For instance, while a heat flux is proportional to gradient of temperature in the Fourier equation, a molar flux is proportional to gradient of concentration in Fick's law. For these two equations to be the same, then the heat flux should be proportional to gradient of concentration of heat as well. So this is achieved by rearranging Fourier's equation as follows. That is equation 5. So what you do is when you get here, write it down, get back to Fourier's equation and see how we rearrange this. Note that rho CPT represents a heat content per unit volume. And this is called, of course, K over rho Cp is called thermal diffusivity, which we mentioned also. So in a similar fashion, Newton's law of viscosity can also be rearranged this way, so that the quantity rho over mu is known as kinematic viscosity. Thus, the rate of heat transfer, momentum transfer, proportional to, and they have the same quantity. Now, Kd and mu, which have different units, alpha d and v have the same unit. So we are trying to show how this heat, mass, and momentum transfer can be made to be the same or look the same. Now, the differences between them, in spite of this analogy, actual mechanism of the 3 processes differs. Heat transport by conduction involves transfer of energy through molecular interactions within a medium without bulk motion. In mass transport, 2 or more components have to be present for the concentration gradient to exist. Momentum transport is even more complicated. So we can see the graduation from one level to the other. First, the momentum flux occurs. Second, while temperature and concentration are heat, mass transfer is scalar, but velocity is a vector. However, the mathematical analogy is important and quite useful. The 3 rate equations can be put in the form of equation 7. So phi is flux of property, diffusivity, and also concentration. We have an illustration. 2 large horizontal plates are spaced 5 cm apart. The space between the plates is filled with benzene at 30 degrees C. The upper plate is moving in another direction, and the lower plate is also moving in the same direction. Calculate momentum flux and all that. So we just applied, just take your time, look at this. We have made this equation, which is the same as this. We substitute, we get, and then force per area, we can now get the area, or we can also get the force since we are given the area. Thank you very much. We've come to conclusion of this module. We've been able to look at momentum transport, Newton's law of viscosity, application in one-dimensional momentum transfer, and then we've looked at analogy between heat mass and momentum transfer. I believe to see you in the next module. Thank you.